Well, today is lesson 8.4, day 2, rational functions. As you can see, I'm alone, and that's because Miss Boyd's son is homesick today. So I really am sorry, but you guys are going to have to just deal with me. Here's the essential question. How do I find the zeros, asymptotes, and wholes of a function? So in the last lesson, we talked about, if you look right here, this equation right here is going to be used today, and it was used in the last lesson. Now remember, I'm going to refresh your memory. H and K, which we're going to find, affect the locations of the asymptotes, the domain, and the range of rational functions, whose graphs are hyperbolas. These equations represent a graph that is in the shape of a hyperbola. So I'm going to scroll down now, and this is just kind of like an extra note, just helping you out. Remember, K is the horizontal asymptote, and this is going to represent the vertical asymptote when x is equal to h. And here is our equation right here. Okay, I'm going to scroll down because sometimes, oh, I can't scroll on that. This is where Miss Boyd comes in handy because now I got to do two things at the same time. And that's difficult. So sometimes you're going to get a function that looks like this. You're going to have a polynomial on top and a polynomial on the bottom that you will need to factor each one. It won't be really nice in this form. So you guys are so good at factoring now. You will be great. So what's going to happen is when you're trying to find the zeros, which are the x-intercepts, you're going to factor your numerator and set it equal to 0 and solve for the x values. The denominator you will factor, set equal to 0, and that will be the vertical asymptote. Remember, vertical asymptote. An asymptote is a line that is approached but never reached, so your values are undefined. So obviously we're going to look at the denominator because you can't divide by 0, which means it would be undefined, so therefore that's where the vertical asymptote would occur. Okay, I talked about zeros, vertical asymptote. Horizontal asymptote, we need to find the degree of polynomial p and q. Remember what degree means. It's the highest exponent. So for example, if I can write over here, if I have x, ooh, yikes, I don't like that big print, x squared plus x plus 2, the degree, this is a 2 by the way, the degree would be a 2. That's how you find degree. Look at the highest exponent in a polynomial. So if the degree of polynomial p is greater than q, there is no horizontal asymptote. If the degree of polynomial p is less than q, the horizontal asymptote is y equals 0. And if the degree of polynomial p equals the degree of polynomial q, then to find the degree, to find the horizontal asymptote, you're going to look at the leading coefficient. So over here, let's say I'm going to throw a 2 in there. Okay, so the leading coefficient would be 2. So I'm going to throw in, I'm going to throw in a polynomial right now. Okay, x squared plus 2x plus 4. Come on. There we go. Just a little delay there. So the degree of the top polynomial is a 2. The degree of the bottom polynomial is a 2. Because the degrees are equal, to find the horizontal asymptote, what we're going to do is we're going to look at the leading coefficient in the first polynomial, which is a 2, and divide that by the leading coefficient in the bottom, which that would be a 1 right there. So the horizontal asymptote would be y equals 2. Here's a little overview of what's going on. All right, so I'm going to go to the next page right now. Some rational functions, including those whose graphs are hyperbolas, have a horizontal asymptote. Okay, we talked about that. The existence and location of a horizontal asymptote depends on the degrees of the polynomials that make up the rational function. I just talked about that. Note that the graph of a rational function can sometimes cross a horizontal asymptote. However, the graph will approach the asymptote, remember, but never reach it. All right. This right here is exactly what I talked about on the first page. It's just a repeat of looking at the degree of polynomial p and the degree of polynomial q and so forth. when P is greater than Q, when the degree of P is less than the degree of Q, and when they are equal. You use this to find the horizontal asymptote, okay? Because remember, to find the zeros, you're looking in the numerator. So that's where you find the zeros, or the x-intercepts. To find the vertical asymptote, that would be, I'm going to call it VA, vertical asymptote. You look in the denominator and set those factors equal to 0. And then to find the horizontal asymptote, you're concerned with the degree of each polynomial. There we go. Next page. Well, it looks like we're ready for an example, and it says, identify the zeros and asymptotes of the function, then graph. Well, we've already graphed it for you, but let's go through. This is what you're going to have to do in this section. Okay, so notice, this is the same thing as, I'm going to write this over here, f of x is equal to p of x over q of x. Okay, so we have p of x over q of x. So remember what I said, we're going to have to factor the top. So I think what I'm going to do is I'm going to go over here, since I didn't leave myself a lot of room. Yikes. And we're going to factor this together. Okay, all over x. Remember, when we factor, there is no greatest common factor here. So what multiplies to -4 and adds to -3? Okay, well, we know we need an x, and we know we need an x. Let's see, what do you think we should use here? Well, I'm going to try, I could do 2 and 2, but that will never add or subtract to 3. So I think I have to do 4 and 1. They have to multiply to a -4, so one's negative, one's positive. And remember, we always look at this then, that goes to the bigger number, which is right there, negative and plus. So -4 times 1 is a -4, and -4 plus 1 is a -3. We are done. So now we have to find the zeros. Remember, the zeros, you look at the numerator. And I'm gonna change colors here. We're really experimenting today. Oh, looks nice. Okay. We're going to set the numerator equal to 0. When we do that, x is going to be 4. Ooh, doing it right there. And the other one, ooh, hold on here. X plus 1 is equal to 0. So you subtract 1 on both sides, and you get x is equal to -1. So our two zeros are 4. I'm going to even try the highlighter here, guys. Let's see how this goes. Ooh, okay. I may just X Miss Boyd out of these videos going forward. Just kidding, Miss Boyd. Anyway, the zeros are x equals 4 and x equals -1. You look at the numerator. The vertical asymptote is, remember, we look at the denominator. Well, guess what? X is equal to 0. Because here, if you look at the denominator, the only time that could ever be 0 is when x is 0. So we don't write x cannot equal 0 like we did in the other lessons. It's asking for the vertical asymptote. So we're telling it it's at x equals 0. And you look at the graph, there it is right there at x equals 0. The horizontal asymptote, I better scroll down a little bit here. Oh no. Yeah, I can do that. Remember, I look at the degree of polynomial of the top. Polynomial P. So let's fix this. So that would be the degree of P. So let's write that. Degree of P is 2. And the degree of Q is 1. We look at the highest exponent. So because P is greater than Q, well, you might have to go back to the other page. If P is greater than Q, there is no horizontal asymptote. There we go. Okay, I'm going to scroll down, and we're going to save example 2 for class. Example 3. I'm going to save example 3, And I'm gonna go actually to example 4 right now. Let's do that. Okay, example 4. I'm gonna jump to that. All right, right away. Remember what we have here. We have f of x is equal to p of x over q of x. It's getting sloppy because it's going slow when I write that. So let's factor it. We can factor the top. Okay, x, and it will be 5 and 3. And because they have to multiply to a negative, one's negative, one's positive, I give this sign to the bigger number, plus, yikes, I'm getting a little messy here, minus. All right, so, and the denominator, it just is gonna stay as x minus 1. There we go. That's not gonna change. So now we have to find the zeros. We have to look at the, remember, we have to look at the numerator. So let's do that right now. So we have x plus 5 equals 0. So x is going to equal negative 5. And we have x minus 3 equals 0. So x is going to equal 3. So you add 3 to both sides. Those are the zeros. You look at the numerator. The vertical asymptote, you set x minus 1 equal to 0. So x is going to equal 1. Now, I'm a little disturbed by the drawing. I'm looking at this graph right now because it's showing the vertical asymptote at x equals 0. So I think this is a typo because the vertical asymptote, and I'm not even going to try to draw a line, should be right. Oh, yikes. Boyd, I'll never make fun of your lines ever again. That's where the vertical asymptote is. It should go through x equals 1. So the horizontal asymptote, let's change colors. Let's go to blue. There we go. I'm going to look at the degree of P. That is 2. X is 2. And the degree of Q is 1. Oh, it's going to be another one like the last one, but that's all right. So because P is greater than Q, remember when P is greater than Q, there is no horizontal really slow right now. Sorry about that. Asymptote. Okay. So let's go to the next page. So I think we're done with this. Sorry, this video might be longer than you wanted, and I'm doing my best here. So no horizontal asymptote. Next page, example 5. Yikes, there's just a lot of examples here. And then example 6 is the same thing. I'm just jumping around here. Then we go on to holes. So we have an example 7, example 8, and okay, there we go. So I think what I'm going to do is we're going to go through and talk about holes really quick and save those other ones for class. So in some cases, both the numerator and the denominator of a rational function will equal 0 for a particular value of x. As a result, the function will be undefined at this x value. If this is the case, the graph of the function may have a hole. A hole is an omitted point in a graph. So the same thing happens for example 7 here. We're going to, number 1, what we're going to have to do is I'm going to write f of x is equal to p of x over q of x. And I'm going to factor over here, okay? So we have x squared minus 9. That is going to be x plus 3, x minus 3, all over x minus 3. So first thing I'm going to do is we're going to talk about the zeros. Let's talk about that first because we're used to that. However, what I'd like to do is, if we go back up for a minute, I forgot to say, if a rational function has the same factor x minus b in both the numerator and the denominator, then there is a hole in the graph at this point, unless the line x equals b is a vertical asymptote. So let's look at the hole first. I see an x minus 3 on top, and I see an x minus 3 on the bottom. When that's the case, so it's something that you can essentially watch. Cancel, cancel. When you can cancel something on top and bottom, the whole is where that factor occurs at. So I'm going to set x minus 3 equal to 0. So the whole is at x equals 3. That is where the whole is. Now the 0, typically, we would say that the 0 would be at x equals 3, and I set x plus 3 equal to 0. X is equal to negative 3. The 0 only is at negative 3 because the whole is at 3. A 0 cannot occur where there is a whole. Also, there's no, in this case, no vertical asymptote because it was crossed off. So there's no vertical asymptote, that's none. And then the horizontal asymptote will be, so let's just write this, the degree of P is, so the top is if you look up there, is a 2, so 2, and the degree of Q is 1. So again, P is greater than Q. We'll do one in class where it's not going to happen like this. I promise you, there is no horizontal asymptote, and this video is getting way too long. We are done with that. Okay, we're going to talk about the rest of that in class. This is class. Video question. Identify the horizontal asymptote of the function. And then number 2, identify the vertical asymptote of the function. Apologize for the long video. We will see you tomorrow.